Okay, good morning, everyone. Quiz on Monday, as usual. Topic of assessment is mesh current analysis, and the homework was due last night. I think almost all students are done with the homework, and several students did reach out to me with questions, and so hopefully it all went well. I will post the announcement about the quiz sometime later today, but again, by now students should be aware that there's a quiz every Monday, and then the topic of assessment will always be the material that was covered in the preceding week. Okay. All right. So one topic that is remaining in the analysis techniques is superposition principle, and we will look at that right now. And then after that, we'll go into the concept of equivalent circuits, and that would be the end of chapter 2, which will be next week. Also, now we have breathing room. We can slow down a bit. The first few weeks are kind of rushed, especially the first week, because we have to cover a lot of the refresher material. But now, we can take it a little bit slower. So, okay, superposition principle. Let's say we have a circuit that has multiple sources, whether it's a voltage source, current source, or a mix and match, 3, 4, 5, 6, 7, 8, as many sources. There could be like n number of sources in a circuit, right? Really complex and large circuit. The superposition principle states that if it's a linear circuit comprising of linear components, you could break up this circuit into multiple pieces, smaller pieces, and you can analyze each circuit with only one source active at a time. Okay, one source active at a time. So if let's say we have two sources in a circuit, okay, voltage source, current source, Vs and Is. And there are, let's say, 4 resistors, R1, R2, R3, R4. So the voltage, let's say voltage and currents that appear in the circuit, let's say it's VR1, for instance. Okay, VR1. The voltage across voltage across R1 would be a result of the voltage source Vs and the current source Is working at the same time. Does that make sense? Right? You have a voltage source Vs and a current source Is present in the circuit. The resulting voltages and currents in any part of the circuit would be a result of both of those sources working together, working at the same time. So superposition principle states you could analyze the circuit by only having one source active at a time, find the voltage or the current that is of interest. Then you turn off that first source, you turn on the second one, you analyze the circuit again. The second source, first source, you calculate the voltage or current of interest, and then the actual voltage or current would be a sum of both those results. Okay, so you break up the circuit into n number of parts, where n is the number of sources that are present in the circuit, and you perform an analysis with only one source working at a time, or one source active at a time. The rest of the sources are inactive, or we like to say reduced to 0. The value of the sources would be reduced to 0. So if you have two sources, Vs and Is, you would perform an analysis with only Vs working and Is reduced to 0. Then you perform a second analysis with Is working and Vs reduced to 0. You calculate the quantities of interest for both sources individually, and then you simply sum them up or add them up together to find the actual value of the voltage or the current. And so R could represent voltage or current in any part of the circuit. And then the actual value of R would be a result of all the individual pieces, R1 plus R2 plus R3 plus all the way so on and so forth until Rn, where n represents the total number of sources in the circuit. Okay. Should probably choose a better variable than R. R is used for resistance, but in this case, it's just signifying either voltage or current. Doesn't really matter. X, for instance. Okay. And then we say that we reduce the sources to zero. Okay. Reduce the sources to zero. So we'll look in the next point how we do that. But think over the first point, the superposition principle, and let me know if you have any questions. Does that make sense? At least the principle. I'll go over in detail with the example and the problem and everything, but at least the principle, just in theory right now, does it make sense? Okay. Okay. All right. So reducing a source or making it inactive is done by replacing it with either a short circuit or an open circuit. Reduce to zero. Let's say you have a voltage source Vs connected between nodes A and B. Okay, connected between nodes A and B. So if you have two nodes A and B and you're measuring voltage between the two of them, that indicates that one point is higher than the other, right? How do we ensure that both nodes have a voltage of zero? Well, both of them have to be at the same level, right? So the way we can do that is by connecting them together. And so we would take out the voltage source. And we replace it with a short circuit wire. This is A, this is B. You replace it with a short circuit. Short circuit means a wire. Wire has 0 ohm resistance. And therefore, I can say Vs now has a value of 0 volts. Vs now has a value of 0 volts. This is the lab that students will perform next week. We use dual power supplies, 2 power supplies at the same time, where the voltage source is reduced to 0. In the lab and also outside of the lab, if it states short the terminals or the power supply terminals to reduce it to 0, it does not mean that you're shorting out the actual power supply. Okay, what it means is you short out the terminals where the power supply is connected on the circuit. So you take those terminals, you take those cables out, and the place where the power supply was connected in the circuit, that place or those 2 points are to be connected with a wire. Okay, when you go to the lab write-up, it will state, and your instructor would also state that. But again, just letting you know, as you know, we are running circuit analysis. If you read or hear the words reduce the source to 0 or short out the power supply, you're not actually shorting out the power supply. You're shorting out the place in the circuit where the power supply is connected. That's what it means. So you remove Vs from your circuit and you place a wire in its place. Thus, you are connecting both those nodes together. If you connect both those nodes together, the difference in electric potential is 0 volts. Thus, you are making Vs inactive. Make sense? And you take that concept and apply it to current sources. Current needs a pathway to flow through. If there is no path, if it's broken, current cannot flow through. So if you have a current source, you simply remove it from the circuit. Once you remove it from the circuit, you don't replace it with anything. Current does not have a pathway to flow through. So now Is is reduced to 0, or Is is inactive. And so for a current source, Doesn't matter which direction that current is flowing. If you simply remove it, we call it OC, open circuit. And therefore, IS is equal to 0 amps. And thus, we've made the current source inactive. All right, take a pause, think about it. Let me know if you have any questions. This, while you think about it, also note, this is not just important for superposition. It's going to be very important for the next topic, that is equivalent circuits. All right, any questions? So far, so good. Okay. Anyone else? All right, let's look at an example then. Determine the current I2 using the principle of superposition. Okay, I2. First things first, locate I2 in the circuit. It is on the far right. It is the current flowing through R3. Current flowing through R3. Okay. Now, what do we see? Wait. Yes. It's in the center. Yes. Yeah. What I was saying was, we are asked to find I2. I2 is the same current that's flowing through R3 as well as flowing through R2. R2 and R3 are in series. Yes. Yes. So, yeah. And we'll build the circuit for both the cases, and then we'll analyze it independently. Just wanted to point out, so students, I know like to take notes in the classroom, but the slides are available on the website separately. So if you're not, if you're not on the class notebook, I would strongly recommend you join the class notebook. Also, the slides are also available from the front page. So you can, if you wish, you can take a printout and just write on top of that. Sometimes it gets lost because there's a lot of information on Canvas and there's not enough time to go through everything. So I thought I'd just point it out. Okay, so here we see that R2 and R3 are in series. It is possible to reduce it before we begin analysis, but I'm going to leave it alone for now. Okay, I will leave it alone for now because every time we redraw the circuit for each source active, the circuit will change. Circuit will change in fundamental ways. Okay, so you keep redrawing the circuit as many times as is necessary for us to understand. So in this case, let's take first the case for Vs being active and Is is inactive. If Is is inactive or reduced to 0, that means we simply remove it from the circuit and don't replace it with anything. Okay, so we draw the circuit out first without Is. And then, of course, in this case, it does not really matter. So we'll just leave it as it is. This is plus minus. And then R1. And then R2. And then R3. And then, as was just pointed out by a student, we have R1, R2, and R3 all in series. This is Vs. Let's write down the values here. So 10 volts, 2 amps, 5 ohms, 2 ohms, and 4 ohms. Okay. And then I will note current I2, but this is the current I2 that is flowing solely due to Vs. So you can label it anything you want, but for simplicity's sake, I'm going to just call it I2Vs. Okay. You could call it IX, doesn't really matter. As long as you specify and you annotate or you note it down on your circuit diagram, that is all the explanation I would require. That's all it needs. Yes. No. Yes, that is correct. So the question being asked is, this I2Vs is not the same as the actual current I2? And the answer is yes, it's not the same. So we would take the first current due to Vs, and I would just label it as I2Vs. We'll take the second current due to current Is, and I would label it as I2Is. And then the actual current I2 would be a sum of both those currents. So we have now broken the circuit down into two parts. One part is where only voltage source Vs is active. Second part is where only current source Is would be active. But what do we see here? In the original circuit, how many nodes do we have? We have 1, 2, 3, and 4 nodes. We could possibly reduce it to 3 nodes and apply node voltage analysis. We see 2 meshes, and we could apply mesh current analysis. Write our equations and then solve those equations. But yes. I haven't come across a circuit where I wouldn't be able to apply. So the question being asked is, can we always apply node voltage and mesh current analysis? The answer is yes. To the best of my knowledge, we can always apply node voltage and mesh current analysis. You can always use mesh. Not in this class though. Because we are, again, I'm required to teach mesh current, and I'm required to assess a student's understanding of mesh current analysis. So if the student doesn't show me mesh current analysis, then I cannot award any credit to that work. Yeah. Well, it specifies superposition. But after, so superposition, again, that's a good question. It brings me to an important point. You have superposition, right? Superposition, you break up the circuit into multiple parts. But after you break it up into multiple parts, you are free to choose whatever technique you wish to apply. So then, yes, it would fall under superposition in that case. But right now, if you look at the circuit on the right, what do we see? On the right. So we have R1, R2, R3. Yep. One mesh, one resistor. We can reduce it down to Req, total equivalent resistance, as seen by the source, Vs. And I can find I2 by applying simple Ohm's law. And that's it. It's a one-step answer for the first circuit. So I can find, change the current, I2 Vs as equal to Vs over Req, and in this case, Req is R1 plus R2 plus R3. Vs is 10 volts, 10 volts divided by 5, 2, and 4, 11, and therefore I2 due to Vs is 0.909 amps. For those of you who are performing the calculation, do you obtain the same value? Yes or no? 5 plus 2, 7, 7 plus 4, 11, 10 divided by 11 gives 0.909. Yes? All good? So then up next is IS. So the second case would be where IS, not second case, sorry, second part of the analysis would be IS active and VS inactive. Now this raises interesting possibilities. So we have R1, we have R2, we have R3, we have the current source. Let's make this larger. And now Vs is reduced to 0. Reducing Vs to 0 means we take it out and we replace it with a wire, short circuit wire. So you draw out the circuit for every step because the circuit changes. It changes fundamentally. And so R1, R2, R3. And here Vs is equal to 0 volts. And this current now is I2 due to Is. Once you redraw the circuit, take 30 seconds. Let it sink in. And do not rush through things. Take 30 seconds, look at the circuit, and see how the circuit has changed. Yes. So it is a power supply. So the question being asked is, how does a current source work, and what's the difference between a voltage source and a current source? Well, let me ask you this: are you taking the lab? Okay. So in the lab, we are using power supply units, right? If you look at those power supply units, you would set the voltage and it outputs some current. If you take that same power supply and you run it in constant current mode, it is now a current source. So in real life, they are one and the exact same thing. The box is exactly the same thing. A power supply unit can supply voltage and current. They cannot exist without each other. If you're supplying voltage, you are supplying current. If you supply current, you are supplying voltage. If you run that power supply in constant voltage mode, it is a voltage source. If we run the power supply in constant current mode, then it is a current source. If you look at those power supplies, again, for those of you who are taking the lab, next time you go in the lab, there should be a small indicator or a small display with the words CV and CC. CV stands for constant voltage mode. CC stands for constant current mode. Almost all experiments in 251, we use those as voltage sources. We do not use them as current sources. So that's the only difference. But in theoretical modeling, especially for audio applications like audio amplifiers, it's very, very useful to model them as constant current sources. Meaning the current level remains the same. The voltage will change depending on what the load is or the circuit is. In a constant voltage mode, the voltage remains the same. Meaning if it's a 10-volt source, it will output 10 volts. Doesn't matter what circuit resistances you connect. The current will change, but the voltage remains the same. That would be voltage source and current source. Does that answer your question? Okay. All right, so what do we see? When IS is active and VS is inactive, what do we see? R2 and R3 on the far right are in series. That doesn't change, right? They're in series. That does not change. But what has changed is on the left side of the circuit where R1 is now connected to IS at the top node. And if you follow that line, at the other end of R1, it is connected to the other end of IS. So both the nodes of R1 are connected to both respective nodes of IS. So they are in parallel. How about the combination of R2 and R3? So combination of R2 and R3 in series is R2 plus R3. You can reduce that to a single resistance, and that single resistance is also in parallel with IS. You can redraw the circuit one more time, two resistors in parallel. So current source IS, two parallel resistor branches in parallel with IS. What happens to that current? It splits up, gets divided. What technique comes to mind? Well, current being divided, current division. Current division. I know it's not everybody's favorite technique. Current division is a little trickier than voltage division. But if you just want to take it 2 steps, again, current division, voltage division are just shortcuts. They're shortcuts, allows you to skip over 1 or 2 steps. If you wish, you can reduce the entire network down to one single resistance, find the voltage across that current source. Because they are in parallel, the same voltage applies across both resistive branches. Then you apply Ohm's law one more time, you find the current I2, IS. Make sense? Yes. Yes, we can. We can apply. Yes. Yeah. Question being asked is, can we do a mesh analysis? And the answer is yes. So once the initial setup of superposition is complete, you're free to choose whichever technique you want. But in this case, current division is like a one-step answer. So if I wish to find Req as seen by the current source is R1 in parallel with R2 plus R3. So R1 is 5 ohms, 5 in parallel with 6. You can perform this calculation very easily. 5 times 6 divided by 5 plus 6. 30 divided by 11 should give you 2.73 ohms. So total Req of R1, R2, and R3 will be 2.73 ohms. Now current division, I2 due to IS can be given by IS times Req divided by R2 plus R3. That is the resistor we are interested in. So IS is 2 amps. 2 amps times 2.73. And then R2 plus R3 is 6 ohms. Surprisingly, we get the same value as before. .909 amps. All right. 10-second pause. Think over that. Let me know if you have any questions. Job's not yet done. Actually, let's take a longer pause. Look at that and let me know what you see. Absolutely. Absolutely, yes. So the observation is that the IS is flowing down. If it's flowing down, then it's coming down here. It's going this way. Splits in two, and basically it's in opposition to our actually measured I2, IS. And so the actual value of I2 due to the current source, IS, is minus 0.909. Yes. Either ways, doesn't really matter. So that's a good observation. Yes, the actual value is, I should put at the beginning. And of course, I'm not including minus at the first because I want to use it as a teaching moment. And so that's why I didn't. But you're absolutely correct. If I'm writing out this equation as a solution to a problem, I would put a minus sign right in the formula itself. Again, the blue arrow is simply indicating the direction where we are measuring the current. Okay. Remember, current always goes from plus to minus, high to low for a resistor, right? For a component. So high to low means my arrow head is negative and the tail of the arrow is positive. It simply indicates if I had a meter to measure that voltage or that current, the positive terminal of the meter would be at the tail end of that arrow, and the negative terminal would be towards the arrowhead. That's what it is doing. So the blue arrow simply indicates if I was measuring the current flowing through R3, my meter would be connected in that direction. That's all it says. The actual current is flowing opposite. So my meter would give me a minus 0.909. Make sense to everyone? Questions? So job's not yet done. I2 is the sum of I2 due to Vs and I2 due to Is. Again, these are just labels and notations. You can note, you could label it as Ix and Iy, and you could say I2 is Ix plus Iy. That's it, as easy as that. And this would give me 0.909 plus negative 909. So my answer is 0. Nope, 0 amps. And in this case, 0 would give you 100% credit. All right. Think over the entire process. We'll take a longer pause and then let me know if you have any questions. Yes. No, the voltage source is providing enough current to create 0.909 in one direction. And the current source is providing enough to create in the other direction. Cancel each other out, yes. Essentially, if you were to calculate the voltage across R3 or across R2 and R3, the voltage at both ends would be 0 volts. That's what it would be. Yes. This one? Current division. Current division. So let me write it down there. You could use any analysis technique. Again, you can use series parallel analysis where you reduce R1, R2, R3 into one single resistance. You apply Ohm's law to find the total voltage, and then you apply Ohm's law again to find the current in each branch. Yes. No. The question being asked is practical application. If you have 0 volts across a light bulb, then it will not turn on. No. Well, 0, I think what you're trying to say is if you had, let's say, an equal amount of voltage at both ends of a light bulb, would it turn on or not? Right? I mean, if it's 0 volts, yes, essentially it is 0 volts. If it's 5 volts at one end, 5 volts at the other end, the light bulb sees 0 volts, it will not turn on. Because if both ends are the same voltage, There's no electrons, there's no current flowing through that pathway. So it's not so much a case of the voltage source sending 0.09 and then current source countering. It's more to the point that the voltage across those two nodes will end up being 0. And that's why no current flows through there. Yes. Oh, you're talking in terms, okay, the question being asked is the saying which says it's not the volts that will get you, it's the current that gets you, right? That's in terms of the, I'm guessing, electric shock to a human body, right? So if you have 200, well, I'm trying to imagine a scenario where you have like 200 volts in each hand and you don't get shocked. Because if you are if there's a pathway for current to flow through your body, then you would get shocked. If so, technicians and engineers who work on like high voltage power lines, they wear this protective, protective apparel that prevents the current from flowing through their body. So let's say there's a high voltage in the US. You might not have seen this, but in many parts of the world, especially India, we have a vast railway network which have overhead power lines, and those are running at 25,000 volts. So you could essentially just hold on to and hang from like using one hand, and if there's no pathway for the current to flow through, then essentially there's no voltage difference. It's an open circuit, right? So if you see an example where we had an open circuit, one end of the resistor is connected to high voltage, but the other end, there's no pathway for the current to flow through. So essentially it would be like a broken circuit. Current cannot flow through there. And so if there is no current flowing through, the voltage does not matter. But if there's a pathway for the current to flow through, then yes, you'd be on fire. Yes. Meaning if I had my hand and my leg touching, I don't think it would make a difference. Well, maybe you might be shorting out. No. If it's 2 power, because it's only carrying 1 voltage, that gets into a whole different area of like, electricity distribution. Let's look at it this way. Overhead, not the overhead power lines, but the long distance transmission lines. It's always transmitted in 3 phases. So you have 3 wires. Anytime you see a long distance power line, like those giant, structures that hold up those power lines, you'll see 3 of them because it's transmitted in 3 different phases. So if you're hanging from one power line and you manage to actually hold on to the other one at the same time, then yeah, you'd be toast because you're not shorting out between the 2 points. So yes, then current will be flowing through. And so, yeah, the current will get you. All right, any other questions? So again, superposition, you analyze with only one source active at a time. Superposition homework only has 2 problems. You can knock it out in under 30 minutes. So I'll go over those 2 problems like right now. If you don't have any class after this, you could possibly knock it out like right now. 2 sources, you have seen this circuit before. The current direction does not matter. The current direction IS is simply indicating that is the polarity of the measurement meter. My meter is connected with the positive end at the tail and negative towards the arrow. Okay. So 2 cases would be where VS is active and the current source I is inactive. So you have voltage source, you have the resistor, and the current source is no longer part of the circuit. And this is exactly the same as the previous one, except instead of a current source, now you have a voltage source. Yes. Yes, it is. It's right at the end, page number 36. Yes. So again, these are the only two problems. There's not much to it. There's pretty much straightforward. Second one is rather straightforward. The first one, again, you have to think a little bit. And here I'm doing the thinking for you, so you don't have to worry about it. And in the second one, you replace the voltage source with a short. Then you have a resistor. And then you have the current source. So again, these are the two circuits. And then if you look at the voltage source is now shorted out. That short or the wire with 0 ohm resistance is in parallel with R1. So the reason I'm going over this is to explain that concept. If you're driving down the street and the road splits in two, one on the right is construction, traffic, debris, and the one on the left is completely devoid of traffic. It's completely open. Which path do you take? The path of least resistance. So it's the case here. If you have a wire in a circuit, anything connected to that wire in parallel is effectively redundant, is effectively does not matter. It may as well not be connected to the circuit at all, because anything that comes, this current source is coming through here, everything will go down this pathway. Nothing will go through here. Even if that resistor is 1 ohm, the wire has a resistance of 0 ohms. So everything will flow down that wire. So anything in parallel with a short circuit wire is effectively not part of the circuit at all. So you don't have to consider R1 in your analysis. You simply solve the circuit with only 2 resistors. This is most of the thinking that is required for the homework, and I've done the thought process for you. So it shouldn't take long to solve this. The second one doesn't require any hints, doesn't require anything. It's just 2 current sources. You simply analyze the circuit with only 1 source at a time, and you find the values of I1 and I2, or Vx, as the case may be. And that's it. Those are the only hints. Actually, there's no hints required. So if you want to keep your weekends free of circuit analysis, you get this done today itself, and Saturday, Sundays, you can, well, I know. College students today, especially engineering students, always have a lot of work to get done. And you have to study for Monday's quiz. But that can be done Sunday night. Friday nights and Saturday nights, go out and enjoy. You know, what they say about engineers, we study hard, we work hard, and we party hard. So if you're not going out on Saturday nights, then you need to get out a little bit more. All right, there's one more thing, not quite yet. Not quite done yet, not for today. 7 minutes left. I want to talk about the concept of Thevenin and Norton equivalent circuits. This is the topic. This is not a new analysis technique, but it is one of the most important concepts in circuit analysis. Okay, most important concept in circuit analysis. A little bit more, a few more minutes before you go and party. All right, so we have this large circuit, and let's say your job as an engineer or a designer is to determine the value of the voltage VR6, and it needs to fit within a certain spec. Okay, so VR6, let's say, is required to be 2.5 volts or so. And then you have multiple sources in the circuit, multiple resistor values. You have to perform an analysis. You don't need to write any of this down. Okay, this is just listen to me talk. Okay, you don't have to write anything down. So you have this large circuit, you have R6 in there. R6, the value is unknown, but you need the voltage VR6 to fit within a certain spec. Your job as an engineer is to find the value of R6. Everything else in the circuit has already been determined. It is fixed. The value of the rest of the circuit is fixed. You need to find one last remaining value of R6. So what do? You analyze the circuit, either node voltage analysis, mesh current analysis, or superposition. You find the value of R6, right? Use NVA, or MCA or SP to determine R6. Then you find the value doesn't fit. Let's say you chose R6 as 50 ohms. So now you get a larger voltage. Doesn't work. You change the value of R6. You analyze it for, let's say, R6 is equal to 30 ohms. It gives you a very lower voltage, very low voltage. That also doesn't work. So you perform a third analysis and a fourth analysis and a fifth analysis. You keep on analyzing as many times as you need to actually arrive at a voltage for VR6 to 2.5 volts, right? So to perform multiple analyses, multiple calculations. Well, that gets time consuming. You don't want to spend all of that time doing that, right? In the late 1800s, around 1880s or 1890s, there was a French telegraph engineer by the name of Leon Charles Thevenin. He postulated a theory. He said that you could analyze the rest of the circuit outside of R6, meaning you don't take R6 as part of your analysis, and you can represent, you analyze that entire circuit only once, and you can represent that entire circuit as a single voltage source in series with a resistor. And that's it. The theory came to be known as Thevenin theorem, named after him. And the theory postulates, again, the theory is basically that you could take the large circuit outside of R6 and represent it as a single voltage source in series with a resistor between those terminals where R6 was connected. This is where R6 was connected. And now, one-step answer to find VR6. You can change R6 as many times as you want. VR6 is simply a one-step answer from voltage division. Is VTH times R6 over REQ. You can take 100 values of R6 and simulate it. You can find the answer in one step. And that is known as the Thevenin theorem. The voltage, that single voltage, represents all of those sources that were present in the circuit. That single resistance RTH represents all of the resistors that were present in the circuit. So VTH is the Thevenin voltage. And RTH is the Thevenin resistance. It is a very important concept in circuit analysis. It is not a new analysis technique. You are not learning a new technique. Okay, you are simply going to apply the techniques you learned previously to determine VTH and RTH. This is a 30-point problem of the final exam. Again, that it has multiple components. It will test everything from chapters 1 and 2. It's the most important topic in circuit analysis. Few decades after Thevenin's theorem, there was an American engineer working at Bell Labs, working with a lot of audio sources. Audio sources or audio require a lot of applications with current sources and current amplifiers. Okay, lots of theoretical analysis using current sources. So he found using a voltage source unsatisfactory. So he postulated his own theory based off of Thevenin theorem, stating that it is also possible to represent that large circuit as a single current source. And that came to be known as Norton theorem. The engineer's name was Edward Norton, like the actor, but not him. Obviously, this was a long time ago, almost 100 years ago. So Norton theorem states you could represent it as a single current source in parallel with that same resistor, RTH. And so this is known as Norton current. And these are the equivalent circuits. That is the last remaining topic in chapter 2. Okay. And we will look at this next week. Now you can go and party. Okay, we'll end class here today. If you have any questions, I have office hours in the afternoon, student hours. Okay, student hours in the afternoon. And then I will see you all on Monday.